Hello. In this short video, we are going to discuss grid control techniques available in CONVERGE. In CONVERGE, you don't need to create a mesh. It is automatically created at runtime. And since the solver and meshing algorithms are tightly coupled, there is no separate file created for the mesh. Unlike other CFD codes, CONVERGE maintains the original surface definition with high fidelity. This means that the volumes and areas are correct regardless of the mesh resolution. And while the mesh is created automatically, you still have full control over the size of the mesh. There are a couple different ways to control the grid size in CONVERGE, but first you must set the base grid. You define the base grid in dx, dy, and dz directions, and we also have the opportunity to visualize the grid in these directions by toggling these buttons. All other grid control strategies are specified with respect to the base grid. We can set up all of the grid control methods in the grid control panel. There are four primary ways by which users can manipulate the grid. The first is grid scaling, which refines or coarsens the entire grid based on the scale you provide. Second is fixed embedding, which refines a specified portion of the grid. Third is adaptive mesh refinement, or AMR, which automatically refines the grid based on local flow conditions such as temperature or velocity. And the fourth option is inlaid mesh, in which you can specify a grid with an arbitrary orientation, spacing, and construction. There are some additional control methods that won't be discussed in depth in this video. Minimum volume ratio, which allows you to configure temporally and spatially varying ratios for cell pairing, and sealing at intersections, which allows you to modify the default settings for sealing and intersection handling. More information about each of these options can be found in the CONVERGE Studio manual. Grid scaling changes the base grid size for the entire domain. Based on the integer you provide, the grid size will either be scaled up or down by a factor of 2. A negative value of the grid scale will coarsen the grid, and a positive value will refine the base grid. You also have control over when grid scaling occurs in your simulation by using a file. For example, you may want to start with a coarser grid and wash out the initial conditions, and then refine it to get more detailed results. This screen shows an example of how we can define grid scaling in CONVERGE. From 0 seconds to 0.3 seconds, we have specified the grid scale as -1, so CONVERGE will coarsen the base grid. From 0.3 seconds to 0.5, the scale is 0, so the simulation will be carried out at the base grid value. And from 0.5 onwards, the grid will be refined. The next type of control is fixed embedding. Fixed embedding refine the grid at specified locations and times to capture regions of interest. Fixed embeddings can be permanent or time-based. The formula for calculating the embedded cell size is the same as that of grid scaling. However, it cannot provide negative integer for the embedding scale. Fixed embedding can add mesh resolution to various locations, and CONVERGE provides several options for different applications, from boundary and region to shape-based embeddings such as the cylinder and box, and even embeddings around the nozzle and injector. Region embedding is used to refine a specific region. For example, we can see the region embedding on the test region, which is highlighted in red with a scale of 1. And boundary embeddings refine the mesh around a boundary based on the scale and number of embedded layers. Here, if we zoom in, we can see there is a boundary embedding around the NACA blade boundary. It is a permanent embedding with a scale of 2 and 1 embedded layers. So that means the mesh around the boundary for 1 layer will be refined by a level of 2. Additionally, for moving surfaces, such as a valve or rotor, the embedding will move with the surface. Shape-based embeddings, such as sphere and cylinder embeddings, allow you to specify a shaped region anywhere in your domain in which fixed embeddings will be applied. This setup shows several examples of shape-based embeddings. There's the cylinder-shaped embedding, to better capture the combustion chamber, And there's also another one here, embedding 10, to capture the nozzle in the fuel spray. And there are additionally some spherical embeddings here around the source to better capture ignition. The next and most powerful grid control strategy is adaptive mesh refinement, or AMR. AMR automatically increases or decreases the grid resolution based on curvatures in field variables. In this video, we can see the AMR going to work around the flame in a hylon burner. And in this example, the AMR helps resolve the interface between liquid and gas in a gearbox volume of fluid simulation. You can activate AMR on a region-by-region basis or in a defined shape, such as a sphere or cylinder. AMR can be activated for a wide range of variables, such as velocity, temperature, pressure, void fraction, and even the species, passive, and volume fractions. Furthermore, there are a couple different ways to determine when AMR should be triggered. They are referred to as the embed type. Value-based AMR, such as the embed below, embed between, and embed above, applies embedding based on the value of a variable you're monitoring. For example, here, AMR will be applied if the velocity is greater than 5 meters per second. For subgrid scale embed type, AMR will refine the grid if the absolute value of the subgrid field for the selected variables exceeds the user-specified value in the given cell. And just like other grid control methods mentioned, AMR can be permanent or it can be activated for a certain time. Here are some more examples of how AMR can be used to refine the mesh. The main benefit of AMR is that it adds a fine mesh only when and where necessary, thereby reducing the overall cell count without compromising the accuracy of the simulation. It significantly reduces or eliminates the time required to do mesh refinement studies. The final way to control the grid is through inlaid meshing. An inlaid mesh is not part of the Cartesian mesh, so the user will have to create one before running the simulation. An inlaid mesh can be made up of cells with arbitrary shape, size, and orientation. In CONVERGE, inlaid meshes are made up of surface triangles and are defined as a flow-through interface, as we can see here on these inlaid boundaries, interface and flow-through. To create an inlaid mesh, go to the Mesh menu in the Geometry dock here, and you either can create a shaped mesh or extrude one from the geometry surface. To learn more about creating an inlaid mesh, please refer to the Inlaid Mesh training on the Convergence Science Hub. Additionally, you can activate or deactivate inlaid cells by using events. In this example, you can see that the inlaid mesh around the spray will only be activated while the injector is injecting the fuel from -12 to 15 degrees. Inlaid meshes will take precedence over the other methods, and you cannot refine inlaid meshes with the other grid control methods. In this example, we can see how an inlaid mesh is utilized around the boundary of a valve to more accurately predict the flow behavior near the wall. And in this example, it's used to better capture the spray coming out of the nozzle, since the cells are more aligned with the direction of the nozzle compared to the Cartesian mesh. For more details on CONVERGE's grid control strategies, please refer to the in-depth training materials and user manuals on the Convergence Science Hub. Thank you for watching.